Okay, good morning. Welcome back. Um, the midterm score should be out by Wednesday or Thursday in the upcoming week. So, how was the midterm? Is it manageable? Um, I will probably post the solution after the score announcement. So if you want to check, you can check then later. Um, Also, today is the last day for the second assignment. If you have not submit your prediction in Kaggle combination, please do so. Um, you have 10 chances for today. Um, so the topic for today, this is a continuation from clustering algorithm that we learned at the very beginning of the course. Um, it's going to be about mixture model, and this is how um, we want to model the data. So basically we have the data, and then we want some parameter that can explain the data. So we have learned this type of problem before with regression, right? So we have in regression, right? We have feature variable, and then we have the target, right? And then we want to find a line that can explain the feature and the target. Now, when we don't have the target, right? When we don't have the target, what we can only do is clustering, right? If we only have feature, we only have clustering, and clustering is a way to organize the data. But here we want to kind of like combine both idea together. Um, we want to explain the data, but our data does not have a target variable. So how can we model the data? And one of the key points for the mixture model is that um, we try not to trust the data 100%. We want to leave a room for improvement. So we want to use mixture model, right? So this mixture model is a way to explain the data. But the byproduct of explaining the data is that you can actually cluster the data together. And we will see how the mixture model can be used for the clustering. So let's start off with some intuition, right? So in probability distribution, right? If you have the data, right? Let's say you plot only the data with only one variable, right? With a feature variable. And then you plot the histogram of it, right? So if you plot the histogram, some of the feature variable would be a bell curve, right? And you can actually see that you can kind of like represent that column, that feature, with just the average and maybe the standard deviation, right? But in most cases, it's not going to be right very simple like this, right? So if we can plot, right, plot the feature, plot the histogram of feature, you are expected to have some variation, right? And this variation, um, cannot be easily explained by only one distribution. So what we want to do, if we want to have many distribution and we want to mix them, and the way that we mix them is basically we have like, let's say mu1, mu2, and then mu3, right? And each one of them is a distribution of its own. And when you combine all of them, right? So you have the distribution using mu1 plus the distribution using mu2 plus the distribution using mu3, then you have the curve that look like the black one, right? So there's no one distribution that can explain the black line, but if we use three Gaussian distribution, we can explain this black line. So as you can see, we can make many models. So basically, the way that the mixture model work is that you start with a basic model. In this case, it's a Gaussian model, right? On the left side is the basic model. And this model can be customized, right? You can change the SD, you can change the standard deviation, you can change the average. And you have these many basic model, and then you want to combine each of the basic model together to get the combined model, right? So each one you have to figure out which mu would be the best. And our job is actually try to find what should be mu1, what should be mu2, what should be mu3 that can explain the black line. So let's start with the definition, right? So the definition, what we have is we have the probability density function f, right? This f is our mixture model, right? This f is our mixture model. And this f is a combination of the substitution f. And the component distribution is f. Well, you can use any probabilistic distribution, but the most common one that people use is the Gaussian distribution. So you have like f1 of x equal to, I believe, 1 equal 2 pi sigma e to the, I think it's like x squared over sigma squared or something like that, right? The Gaussian distribution. I don't remember the exact equation, but it should be something like this, right? But you can use any other probability distribution function, the PDF, and your mixture model, right, is a combination of this component distribution. And not only is a combination, you can introduce the mixing weight, right? You can introduce the mixing weight. Now this weight, it has to be greater than 0, and the sum of all the weights should be 1, right? And this condition is necessary so that the distribution f can also be probabilistic distribution, right? Because if the pi k, the mixing weight, does not sum to 1, you have something that is not does not follow the probability distribution. And so this is our setup. right? We want to find this function fx that can explain the data x, right? However, we cannot have just one model. We want to have many models, and this number k is the number of components. You pick the number, um, whether it's going to be like 3 or 5. So it's similar to what you did in k-mean clustering, right? You pick the number of cluster first, and then you perform the k-mean clustering algorithm. Here is the same, right? You pick the number of components that you think is enough to explain the data, right? So for here, your main objective is try to explain the data. So naturally, the higher the k is, the better, right? So have you heard of the Taylor series in calculus? The Taylor series is basically is a way for you to make one function as a sum of infinite. It is an infinite sum of something. So the something in the Taylor series is actually a small part of a function. So here we want to combine the small part of the function. So the more part you have, you would be able to explain the data better, right? So in physics, let's say you have a signal, right? A signal in physics. And the way that they explain this signal is by the sum of the sine function, right? Omega x, maybe a, right? So ai omega I x, and this is the basis of the sine function, and then you can combine them many times to recover the original signal. Now here is the same, right? So if you have a large K, you should be able to explain the data almost perfectly. So because of this, right, you can pick the K to be very large, right? If your goal is to explain the data, you can pick the K to be very large so that it's enough to explain the data very accurately. But if you want to use the mixture model for clustering, right? For clustering, so basically, you would think that like the data become like cluster 1, cluster 2, cluster 3. So if you want to use this for clustering, then you may not want a high number of k, right? You want to just enough. And we will see later how we can pick the k so that we have a good amount of trade-off. So given a set of data, right, we would like to find what is called a basis distribution. So the basic distribution is basically the FK, right? Each of the FK, we want to find the FK. And if we use the Gaussian normal distribution, you would have two parameters to for this function, which is the average and the standard deviation, right? The mu and the sigma. And because this is the clustering, so we want to use the mixture model for clustering. We don't have access to y, so we only have feature, right? We have only the column for feature. And this is like the example of how you would do the cluster. So if you use k-mean clustering, right? If you use k-mean clustering, each point in the data must belong to some cluster, right? And at every iteration of k-mean clustering, you just calculate the new mean, and that's it, right? So in k-mean, you already have the centroid, right? For each model, you have the centroid. Now, for the mixture model, we want to have the sigma as well, right? Not only we have this cluster, we know that the center of this cluster is here, but we want to see, is it dense or is it sparse? So we introduce one more, and we will see why we need to introduce this one more parameter per cluster. So in the k-mean, what we did is we did a hard assignment. What do I mean by hard assignment? Hard assignment is that one point must belong to one cluster, right? One point must belong to one cluster. So in the k-mean clustering, right, you compute the distance from the point to the centroid of each cluster, and then you pick the cluster that are closest to the point, right? And then you just assign it to that point, right? So the ZI is basically the label, like the cluster number of that data, right? This is the k-mean clustering. Now in the mixture model, right? So if we calculate the distance, right, 0.2, 0.8, 1.3, then for uh, for the k-mean clustering, you would pick the one with the smallest distance. So this is the hard assignment, right? You use argmin. Now in a mixture model, what we are doing is we are doing a probabilistic model. So we're not asking which cluster this point belong to. We ask a different question. The question that we ask is, what is the probability that this point is generated from this cluster, right? So what we want to find, right? We want to find the probability, the probability that this data, right, is generated from cluster I, from cluster J, let's say, right? And how can we calculate this probability? So remember that when we want to model the distribution, right? We pick a Gaussian distribution, right? We pick the Gaussian distribution, and this Gaussian distribution have both mu and sigma. So if the point is here, right? If the value of the feature is around here, you can see that for C1, you have this, the probability of this point belong to C1 is around here. And the probability of this point belong to C2, you have is around here. And for C3, it may be like very low. So when you define the basis distribution, right? This basic distribution also have the property density function And you can plug in the value to check how likely it is that the point is generated from that distribution. And so for us, right, we can use the model that we construct to calculate the probability that this point belong to which cluster. So what we have now is we have three number, right? If we have three model, we have three number, and each number is going to represent the property that this point belong to each of the cluster, right? Each of the model. So we don't actually assign point to a cluster, but what we can say is this point is more likely to be in cluster 2 than in cluster 1 and cluster 3. Right? So we can compare the probability, the value of the probability. So we have to keep track of more variable. Right? In K-mean, one point only have one label. Now, in mixture model, one point, you have K number of probability, right? And this probability that you have to keep track of is going to be part of the update equation for the model parameter later. And the important thing about these three number is that it must add up to 1. We still want to assign point to a cluster. So the property that this point belong to any of the cluster must be 1. And because each cluster is independent, the sum must become 1. Right? So make sure that the three number is 1. Right? So this is a soft assignment. It's the different from K-mean, right? K-mean, you know which cluster it belong to. And when you update the centroid of each cluster, you only take the average of the point that belong to that cluster. Right? But for here is going to be a little bit different because we don't assign point to only one cluster. So we have the degree of membership, right? So we have the CI, right? Now CI we have K number, right? K is the number of model, the number of cluster. So the property in here, how do we compute, right? How do we compute? So what we want is we want this probability, right? The probability that the label, right? The label equal to the K cluster given my data xi, right? So this is a conditional probability, right? The probability of this point belong to which cluster is basically the probability that the label is equal to K given that I have seen this data. And by Bayes rule, the property of C given X equal to the property of X given C times the property of C divided by property of X. And the property of X, well, you can sum, right? You can condition it again by Z, and then you can sum it up, right? So you sum over C, the property of X given C times the property of C. So our final equation is here. So to compute the CI, right? So basically, this the CI for each for each label. We need to know two things, right? We need to know the probability of the data given the model, right? And the probability of the model itself, right? So basically, we need to keep track of these two variables. So how can we compute each one of them, right? What is the property of X given C? The property of X given C is modeled by the property distribution. So if we pick the normal distribution, or basically a Gaussian, then we can just use the property density function of the Gaussian for this. So in normal distribution, you need to know two things, right? You need to know the average, basically the mean, and also the covariance or the standard deviation, basically, right? And then you just plug X in the function given these two parameters, and then you get the number, right? So if you look at distribution like this, if your feature value is around here, if your X is around here, then it's really likely, so you get higher number. But if your X is over here, then you have the lower probability. Okay. So this is the way to calculate the probability of X given C. Now, what is the property of Z, right? So the property of C is basically if you don't see the data, right? What is the property that the new data that you have no idea about? What is the property that it will belong to this particular cluster? So if we are doing k-mean, basically we can count the number of point for each cluster, right? So in k-mean, if k1 have like 10 point, C2 have 15 point, C3 have 20 point, then the property of C equal to 3, it would be like 20 divided by 45, right? We have 20 point in the third cluster, and then we have 45 point total. So if you pick a point random in the feature space, you have 20 over 45 probability that it's going to be in this cluster. But because we are doing the mission model here, each point does not belong to any cluster, but each point have a probability of belong to each of the cluster. So what we do is we just sum up the probability of C given X for all the label that we want, right? So the probability of the label being 1 is the sum of the probability of each of the point belong to the first cluster, and then you sum it up, and then you take the average. So what happened here? So first we want to find the property of C given X, right? the property of given C given X, you need to know X given C and C, right? And then when you compute X given C, you come back to property of C given X. So it becomes full circle, right? You want to find P of the C given X, but you need to compute P of X given C. But to compute P of X given C, you need to know property of C given X. So it becomes full circle. How can we break this circle? How should we break the circle? Right? So we want to find this, but you need to know this. But to compute this value, wait, actually you need to know this and this, right? Two things. But to know this, you need to know the property of X given C. Right? Oh, wait, I think I flipped the wrong one. Hold on. So I need to know the property of C given X, right? So I need to know the X given C. So this is already solved, right? There's no looping. But for here, right, the property of C, you need to know the property of C given X. So this and this are the same, right? So what happened here is the definition become circular. So to break the circular, we have to do it iteratively. So what happened here is that you cannot compute this by just one time, right? Basically, you can think of it as if you want to compute this at iteration I, then you use this value from iteration I minus 1. So what happened here is that you need to have some value, right? So you need to have some value. Maybe you can randomize, I don't know. But after you have this value, then you can compute the property again using the old value. So that is how we will break the cycle. So we need to do this iteratively. And so what we have so far, right? We know the property of X given C, right? Is this one, property of X given C. And this is defined by the normal distribution, right? So if we know mu Z and the sigma C, then you can compute this, no question. And at the start, right? At the start, we will assume the probability of observing cluster. So at the beginning, right? We say that the property of C, we need to, compute all of this together to get the property of C. But at the start, we have to assume something, right? So at iteration 0, right? At iteration 0, we assume PC to be some value. Most of the time, you pick this to be like 1 over K, right? You have K cluster. So the property of this point belong to any of the cluster would be equal. right? So you can start from here. So if you know these two probability, then you can compute the membership probability. So once we know this, right, we can use this to recompute the property of C, right? We can compute property of C. And we can also use this to recompute mu and sigma so that we can recompute the property of X given C. So I will go with the detail a little bit later, but for now, at the start, this can be computed using this equation. The property of C is assumed. So what do we want, right? Ultimately, we want to find mu, sigma, and pi, right? So you want to find all these parameters. So you start with, this can be, like, this can be random, right? All this can be random, right? You can random them. And you want to find all these parameters that best explain the data. So how can we find them? Right? So if we want a supervised learning, right, we have information about the class label. So estimating the mu, the sigma, and pi would be very easy, right? Because if you know the class label, right, you already know the CI, right? You already know the CI, right? So it's based on the label. But if we don't have CI, so we have to also find the cluster assignment. So the cluster assignment is not part of the parameter, but it is something that you need in order to compute the best parameter. Right? Because in K-mean, right, when you do K-mean clustering, the parameter in K-mean is the centroid. Right? Each centroid is the parameter. And the assignment is actually a byproduct of the algorithm. Here is the same, right? The assignment is also a byproduct of the algorithm. What we really want is we want just to find this parameter that can describe the data. So how do we estimating the C, right? So we start with C first. So if we have, let's say we have 3 clusters, right? We can use base rule, right? So the property of C given X, right? The property of label being 1, given that I've seen the data, is the property of just C times the, this is the property of X given C, right? So basically, the basis distribution, and then you divide it by the property of X. So we want to estimate the assignment. So when we want to estimate the assignment, we fix every other parameter that is not related to C, right? So we fix the mu, we fix sigma, we fix pi, right? So this is similar in the step in the K-mean when you want to compute the assignment, right? You fix the centroid, and then for each point, you just compute the distance to the closest centroid, and then you update the label of that point, right? This is the same, right? You fix the parameter of each basis model of the fix the parameter of the basic distribution, and then you compute the property that this point belong to each cluster. And it's important to note that when you actually do this calculation, you don't have to compute the property of xi, right? Because it's basically, because we know that all of them have to sum to 1, we can compute this product, right, for each one of them, right? Let's say if you get like 0.2, 0.8, maybe 1.3, right? You multiply the probability. And because you know that all of them have to sum to 1, you can just sum it up, right? So when you sum it up, you get 2.3, and then you can use 2.3 to be the normalization term. So in general, people don't compute px, they just compute the product, the property that so this is the prior, right? The prior probability. Basically, if you don't know anything about the data, what is the chance that this data belong to this cluster? And then you multiply this by, if you know the distribution of this cluster, what is the probability that this point belong to this cluster? So that is the step for estimating the Z. Right? So you get 3 numbers for C. And if you want to estimate mu, right, the average of each of the model, then you can fix, basically you fix the assignment, right? You fix the assignment. So you fix the property of Ci, right? So basically you fix this, right? Because you just compute this, right, by fixing the mu, the sigma, and pi, and you want to find the best pi, so you have to fix what you just compute. So you fix the property of Ci equal to k given xi, right? And you use what you compute from the previous slide as part of the equation. So on the left side, I show you NDA. I think it's naive, what is it? Something assignment. Naive, I think it's distribution, right? Oh, it's the naive density assignment, right? So this is the equation that you use in K-mean, right? The centroid of each cluster is the average of all the points that belong to that cluster. Right? So if I have like cluster 1, cluster 2, cluster 3, like if this point belong to C1, then this point will be in the equation for C1. Now in the GMM case, in the mixture model case, you still compute the average, right? This is the average, like xi over n, this is the average. But each point will contribute to each cluster, right? So before one point belong to one cluster, so it will just be in one equation. But for this point, right, you have the property of this point belong to cluster 2. The property of this point belong to cluster 1, but the property of this point belong to cluster 3, right? So you have these 3 probability, and each of the probability is going to be the weight that you put in. So each point will contribute a little bit for each of the cluster based on the property that this point belong to that cluster. So this sum, you sum all the point, right? So sum to n. For the k-mean, you only sum up to the number of points that belong to that cluster. So that is the difference, right? You have the coefficient, basically the weight, right? You introduce the weight to the average. Right? So that is how you compute the new centroid, basically, but with soft assignment. How about sigma? So for sigma, right, it's essentially xi, right? It's actually xi that belong to that cluster, right? It had to belong to that cluster, and then you just compute the standard deviation. Now in GMM case, we still compute so this is the same as this one, but for each point, right? For each point, we kind of like split the point for each cluster. So we have to subtract the mean, right? We have to subtract the mean of that cluster, and then you have the coefficient, the weight, that is the property that this point belong to that cluster. So this weight is the same weight as this one, right? So we will have this value for all the parameter of the model, right? So for the NDA, you don't have to minus the mu k because you know exactly that this point belong to this cluster. So when you compute the standard deviation, you can just use the full point. But for the mixture model, you have to subtract the mean so that you can contribute 1 point to each of the cluster. So because this one you know exactly that it belongs to this cluster, so you don't have to worry about the mean. But for this one, you have to subtract the mean because the weight is conditional is half the label, right? So the label k and the mu k have to match. So what about pi, right? So for pi, if you use hard assignment, right, it's basically the number of the point that belong to that cluster divided by the total number of points. But for GMM, right, each point is going to be split into the fraction, right? So each fraction will belong to each of the cluster. So it's basically you sum the property that this point belong to each cluster for every point, right? So this one you can sum it like this, like family of I to n over k times 1 divided by n, right? And then because this the hard assignment, you just sum 1. But because this one is a soft assignment, right? It's not 1. You're not 100% sure that this point belong to the cluster. So you sum the probability that this point belong to the cluster. So we can keep repeating the process, right? We have three process, right? Estimating C, estimating mu, estimating sigma, and estimating pi. So we can repeat the same process until we want, when we want. But it might be good to have some measurement so that you know when to stop, right? You can pick the number of iteration that this can go. So what we have here is we have the likelihood function, right? So our ultimate goal is to estimate the parameter that can explain the data very well. So we want to compute how well it is that the parameter that we compute explain the data. So we are going to use the likelihood function. Does it look familiar? Right? It's the first question in the exam, right? So what is the likelihood function of the model, right? So the likelihood function of the model is given by, right? So we have the data, right? So given we have seen this data, what is the likelihood that this model come from this data? And the equation is by you multiply f of xi. So xi is the data, right? Xi is the data. F is our mixture model, right? And if you plug in xi to the mixture model, it's gonna give me the probability that this data come from the model, right? And then you multiply the probability of every data point. So it's not the sum, but it's the product, right? It's the product of the mixture model when you use the xi as the parameter, right? So, and this, the f, the picture model is the sum of this by definition, right? It's the definition that we start at the beginning, right? Right here, right? We have the mixture model is the sum of the smaller component, right? So what do we have here is this is the smaller component, right? Or the basic distribution. And what we want is we want to compute the log of the likelihood of the function, right? Because when you multiply a lot of number, it's going to be very hard to compute. So we take the log of this entire expression, right? Of this entire thing. So when you take the log of the product, right? So log of A times B equal to log A plus log B, right? The product become the sum. So this product here is going to become the sum, and then the log is going to be over the remaining of the function. So this is the log likelihood function. And this log likelihood function explains how well the model that we compute explain the data. So we want this to be as high as possible. You want the log likelihood to be as high as possible. And when you do the estimation for each of the parameter, you can compute the log likelihood at the end of each step. And then you can see the improvement, right? It's going to be something like this. And when you see that there is very little improvement on the log likelihood function, you can stop your algorithm so that it does not overfit the data. Right? So this is the way that we check if our estimated parameter can explain the data. Right? We don't have this for k-mean. What do we have for k-mean? For k-mean, we only have the sum of the distance, right? And our objective is to find the centroid that minimize the sum of the distance, right? But for here, we are not actually optimizing anything, but in hope that when you estimate this parameter, it's going to explain the data better because of how we set up the probability. And to summarize the GMM algorithm, at the start, right, we choose K. We choose the number of model. And then you initialize the mu K, the sigma K, and then the pi K. So mu and sigma is the parameter for the normal distribution function, right? The probability density function for the Gaussian distribution. And then the pi K is sometimes they call it a bias term, right? It's the probability that, a random point belong to this cluster. And if you have the data that look like maybe a lot of point in this area, and then we have like some point here, some point here. So for cluster 1, 2, and 3, maybe the pi 1 would be like a lot higher than pi 2 and pi 3, right? That can be the case as well. But in general, the choice of initialization, people would just pick at random, right? Pick at random, especially for mu and sigma, right? They would pick at random. For pi k, sometimes if they don't want to have a bias, they will pick 1 over k. But if they think that there might be a bias, they can just randomize the pi k. And then you repeat the same process, repeat the estimation until the likelihood convert, right? So the condition for the likelihood convert is we have the log likelihood function, right? And if the log likelihood function improve very small, right? So you set some threshold value, and if the improvement is less than the threshold value, then you can stop, right? And then the process that we estimate the soft assignment, and then we estimate the rest of the parameter, right? It's going to be 2 steps inside, right? So this is similar to k-mean, right? For k-mean, you compute the assignment, like you assign label, right? And then you recompute the centroid, right? If this were k-mean clustering. But for GMM, you have more more variables. So the byproduct of this algorithm is not only that you have all these parameters that you can explain the data, you also get this probability, the soft assignment. So you can use the soft assignment for clustering, right? Basically, you just pick the highest probability, or sometimes you can use the non-deterministic assignment, right? So basically, if let's say the property that c equal to 1 given x equal to, let's say, 0.1, c equal to 2 given x is 0.2 and then is 0.7, right? So normally you would pick the one with the highest probability, right? Like in general. But you can do it stochastically by using like a random number generator, right? So if you run the algorithm 100 times, this point will belong to C1 10 times, belong to C2 20 times, and belong to C3 70 times, something like that. So the soft assignment, you can do it using a random number generator. So basically you just randomize some number, right? And based on the property that you have, you just assign it to that label, right? So you can assign it um, using the probability distribution. So that is um, the mission model for clustering. It's another way of clustering, but not only that you got the cluster, you can also explain the data using all this model, right? Because in K-mean, you only have this one, right? You only have the centroid, and it's very hard to explain the centroid. But now you have more, right? You have the sigma as well, so you can explain how each centroid is distributed. Right? Any question? Okay. So if there's no question, we will take about 5 minutes break, and then we will come back with some coding for the GMM. And we also look at how we can pick the K, right? Of course, I haven't taught you how to pick the K, right? So we come back at about maybe 10:10. Okay. So we are going to do some coding for the mixture model. Um, so first let's load the data set. So I want to um load iris data set. So the other data set should already um be in the scalar. So I can say from scalar import data set, right? And I can say the data will be equal to the data set dot load iris. And we are going to use the first two feature so that we can plot it very easily. So it's going to be data dot data. I think the first two would be something like this, and then my y would be the target, right? Okay, let's see. I can print x and then I can print y. So let's see how the data will look. Okay, so um I think so. The first I only have so the target, right? I already know the assignment, right? Basically, which group the data belong to, but I think I got the data not correct. So if I get my entire data, okay, so each data will have four features, right? So I want all the data, but only the first two. So this should give me that, right? Okay. So I have all of these feature, right? And then I can plot so that I can see how the distribution work. So I want to plot x. So I have to import matplotlib, and then I scatter plot x with the first and the the second feature, right? So I have something like this, right? So if I know why, um, the cluster would look something like this, right? But if I don't have the cluster, then this is my basically my data. So if the data only have like two dimension, you would think that there would be like like one group here, and then the second group would be something here, right? So K would be somewhere around two. So the way that we start the the mixture model, so sklearn also have the GMM model. So we want to perform GMM on X, right? So I can say from sklearn dot mixture, I can import Gaussian mixture model. Right. Oops, import just Gaussian. Okay. And then I can say model equal to the Gaussian mixture, and then you can pick the number of component. So I think we try two first, right? Have like this one on the left, top left side, and then the bottom right side, right? And then I fit X. right? And then I can get the assignment equal to model dot predict x, right? And then I will print C and see how it does. So I pick the number of comment in 2, and when I get the prediction, right? When I do the predict x, the model actually predict the cluster for me, right? The model to predict the cluster for me. But what I want is I want to see the solve assignment, right? I want to see each point belong, like what is the property that each point belong to that, right? So the prediction actually pick the best one already, right? They pick the most probable label. So I want to get the solve label from the GMM, right? So there's a function, right? It's not plot yet. So we have the model dot predict proper. It's basically the prediction probability. So in my print, see from here, what I will get is I will get two numbers, like for each point, right? And each number is going to, correspond to the property that this belong to cluster 1 and this belong to cluster 2. And as you can see, like some of the points are like very dominant, like very close to 1, to cluster 1, and then very, very small, like e to the minus 17 is like time 10 to the minus 17. So we can get the solve assignment from this function, the predict proper, right? So you have two function, right? So you have so model dot predict x. So this is going to be your solve assignment, and then this one will be your hard assignment. And then if we want to plot, right? You want to plot using the hard assignment. We already have this plot, so I'm going to do the same plot, but I would say the color would be the C, right? So we have something like this, right? So that is what we would expect, right, from the mission model, right? We think that if we pick k equal to 2, you would have the cluster on the left side and then on the bottom one. So let's compare this with k-mean, right? We will have the same result, right? So we want to try k-mean, right? So we have scalar dot cluster import k-mean, right? And then I pick the same, right? I pick two cluster. I get this is the hard label from the k-mean, and then I do the plot, right? So k-mean, you have the still different result, right? Because depending on your starter point, right? So if your starter point, like the first cluster, the starter point is around here, the second cluster is around here, then maybe you might get this image for k-mean, right? But from here, it's happened that the centroid would be around here, and then the centroid would be around here. So for the k-mean, there is like if the two cluster like overlap a little bit, it's gonna split halfway. But for the Gaussian, like you can mix them, right? The point in around this region in the boundary, it would have like about equal the probability of belong to each of the cluster, right? So the boundary you would have the different probability. So that is how you do the Gaussian mixture. Now, how do we pick the K? Right? That is the main question. Now in K-mean, do you remember how do we pick K? Using elbow method, right? So you have some distance function, right? You compute the distance of all the points to its corresponding centroid, and then you look at the graph, right? You at the graph. For GMM, you kind of have the same, but because for GMM, what you have, right? You have this the likelihood function, right? You have the likelihood function. So at the end of your algorithm, you can compute the likelihood function for each of the K, right? And then you can plot the likelihood function of the K and you can pick the K from there. However, for the mixture model, there is another criteria. It's called BIC, Bayesian information criterion. And for the Gaussian mixture, right? If you search the Gaussian mixture, it has this function BIC, Bayesian information criteria, right? And this, if you go to the equation for the BIC is minus 2 times the log of the likelihood, right? So we have the likelihood function for the GMM, right? You have the log likelihood function of the GMM. And then you take the minus, right? So that is how well your parameter explain the data. But as we establish that having more model, right? Having higher K would allow you to explain the data better. Like, this is always the case. So for the BIC, they have this term. This is the penalty term, right? Is the log n times d. So what is n? N is the number of data. So it's always constant, right? The most important is d. D is the number of parameter. So if you pick k equal to 2, how many parameter do we have to estimate? So we have, for one cluster, you have mu, you have sigma, and then you have pi, right? So for 1K, you have 3 parameters. So if you have K equal to 2, you have 6 parameters, so D equal to 6, right? So it's tied to balance between how well you explain the data and try not to overcomplicate the mixture model. So because the log likelihood, we established before that the higher the better, right? It's more likely that this data is generated from the parameter that you compute. But here you have minus, right? You have the negative. So you want BIC to be low. But if you have more parameter, this term is going to go up, right? So it's the balance between how well you explain the data and the number of parameters in your model. And we are going to use the BIC to help us pick the appropriate K. So we are going to use BIC, right? So we will compute BIC for each K, right? So we start with empty BIC, and then for K in range, maybe I start with 2 and then go to 11. So K equal 2 to 10, right? And then I create the model for each K. I fit the model, and then I use the BIC value, right? I append it to the BIC, to my array, to my BIC array, and then I can plot, right? So it's going to take a little bit of time, right? And then you can do the plot. So we have the BIC from K equal to 2 to K equal to 10. And this is the plot that you have, right? So in here, right, you want your BIC to be small because it's the negative of the log likelihood, right? And so if you see the graph like this, what would you say about the K? You would expect it to be similar to K mean, right? When it's gonna go down like this, right? But for here you have something like this. How would you access this graph, right? So let's try K equal to 3 for this one, right? So this is the image for K equal to 2, right? If I use K equal to 3, I will get something like this, right? So you split the big group into smaller group. And what it actually does is that, well, if you increase, right? If you increase more, maybe 4, right? You're gonna have this as another model, right? So what you see is that having more model does not really improve the explainable of the data very much. And we want the PUC to be very small. So if you see this graph, then yeah, 2 is the best because 2 have the lowest BIC value, right? So if you see a graph like this, don't be surprised. It's very common, because if we don't have the penalty term, it's gonna look similar uh to K-mean. But because we have this term, right? So it's gonna have more penalty because we have a lot of data. And if we introduce more, it's just too complicated, right? And as you can see, that these two distribution, the purple one and the blue one, are very close to each other. So it's better to just combine them, right? It's not good to have it overlap. So that is how you pick K for mission model, right? You plot the BIC, right? Luckily, they already have the BIC. Another one is the AIC. So the AIC is basically straight up just penalize the number of parameter. So for the BIC, you still have the log n, the number of sample as maybe some to amplify the D, right? But if you only use AIC, right? If I change it to the AIC, right? Right, you will still the same, right? You will still pick two, but there are also some interesting case like 6 and 9, right? That is the local. So let's see what does 6 look like. So we went to 6. So it's basically slightly better than 5 and 7. Um, but as you can see, right, this cluster and this cluster, the cluster can overlap, right? In K-mean, the cluster will never overlap because you actually separate the area, right, with K-mean. But for the mixture model, you can have the mean too close to each other, but you can have the sigma, right, the standard deviation to be very large, so the two cluster can overlap, right? And so the dark green, it should have been around here, but um, the sigma is very large. And then for the yellow, you have the mean to be very close to the green, but have a um, smaller sigma. So based on like both AIC and BIC, we can assume we can say that like k equal to 2 would be the best pick. Another interesting plot is that if you want to plot the model, right? So right now we only plot the data with the label. We want to try to also plot the model itself so that you can see the distribution. So now in order to plot, okay, let's say go back to K2, but you want to plot like point here and then maybe some circle here, point here to and then circle here to actually show, because in the K-mean you can plot the centroid, right? You can plot the centroid, but here you also have sigma, and then you want to show the sigma in your graph, right? So you want to also plot uh, this, and the way that you plot, you actually need to do uh, some computation, right? So we have the scatter plot for this, and then so we want to plot the model parameter on the graph, right? So we have to plot the ellipse, right? Basically, it's a way that when you want to plot some Gaussian distribution, you have like the center, and then you have the circle around. The the ellipse around would indicate the standard deviation of each of the axes. So I import the ellipse. I'm going to define the function, right, to draw the ellipse of, right, and then you have the position and then the covariant. So remember, the position is the mu, and then the covariant would be the sigma from the model. So that so I will say covariant. I think that's too much. Okay. So I can compute, basically I compute the I have to import numpy. Okay. Import numpy as np, right? So I compute the eigenvector. So basically what I did is I have this data that are in the same cluster. I want to basically perform PCA, to find the main axis. That would be the axis of the ellipse, like the main axis of the ellipse and then the secondary axis. So I compute the eigenvector, right? And then I can have, I compute the theta, which is the degree between the two vector, and then I can plot the ellipse. So the ax here, I also need the ax, which is the axis that I want to plot, right? Okay. So now that I have my drawing function, I can plot this one. So what I have, let's see. So I have the model, I fit the model, okay. I might have to copy this down here. So it's put in the same one. Right, so I draw the first model and then I draw the second model. Okay, so it will look something like this. So the first model, the centroid is around here, right? And then you have the distribution for the sigma in both x and y, right? So you can draw this angle. Especially you might want to draw the line, draw the dot, the data first, so that the ellipse is on top. Okay. So this is how you present your cluster. So not only the cluster that you present, you can also present the parameter in this way. So as you can see, the variant of the second cluster is a lot bigger than the first cluster. And the length, here, I would say the principal axis of this one would be the one with the highest variant of the data that belong to the same cluster. So that is the coding for GMM. It's very straightforward except for drawing the ellipse. So I just you just copy this code to draw the ellipse, and then you can also get the mean and then the covariance from the model directly. Okay, and before we go, let's check the Kaggle. So our assignment 2 is this one. Let's check the leaderboard. So right now, our highest is about 77% accuracy. Right, basically is the accuracy. And then the lowest one would be 55%. Right. So if we compare this to last year, I should have my last year, I think this one, no, this one. So I use the same data set as last year, and the leaderboard from last year is around here, about 81%. This is the private, so let's see the public. So the public can go up to 86%. So there are many ways that you can convert like this data into a feature vector, and you can try many ways. to compute. So I just show you just TF IDF. I think some of them use like transformer. You can also use transformer, you can use bird. There are many way to compute. So you can keep trying. And for the score, so basically I will pick the score would be the average, right? The average of the score of everyone. And if your score is above average, you will get full point. And if your score is below average, you will get some fraction. It's basically let me type equation. So let's say so the accuracy, let's say is 0.8, 0.79, 0.78, 0.75, 0.6, something like this, right? I will calculate the average of the accuracy first. And then for each one, right? So the average, let's say, is 0.744. So all the people here that get above 0.744 would get full point. And then for the people who get 0.6, it's going to be their score is going to be like 0.6 divided by 0.744 and then time the score for the assignment. So we have public and private, right? So the public will contribute 5 and then the private will contribute another 5. So if you got like 0.6 among this ranking, right? Your score for public, you will get 4 point something, right? 4 point for public. And then for the private, right, I'm going to add the score for the private. Right, so private, I will also compute the average for the private ranking. And then for everyone who got above average of the private ranking, you get 5 points. And then if you are below average, you get some fraction. So so you might get like lower than average public, but sometimes you get higher in private because you don't see the result for the private until after the submission, right? So this is also the case for the first assignment as well. So we have the leaderboard for the public. You have this score. So I will also compute the average of score. And then for everyone who got above, who got below. So this one is like lower the value, the better. So the one who got below average will get full 5 point, right? And then for the private, right, I will also do the same, right? So someone would get like, let's say, this person, right? In the public, they are like in the last spot, but in private, they got the second spot, right? So basically, you want something in between to get full point, to balance between the public and the private. Is that clear? How I compute the score? For this one, it's going to be a little bit different because I cannot just use the score divided by the average, right? Because you would want the lower the better, so it's going to be the opposite, right? So the average would be here. Like let's say the average is this number, right? The average will be here, and then you are, let's say you get this value, and then you will get the value here. So your score for this would be like 4.99, which is still good. Okay. So I will upload. I will update the score for both assignment after the submission for the second assignment. So I will update both at the same time. So any question about the score? Okay. If not, that is for today. And then next week, we will learn more about the classification. And then we will have assignment 3 is going to be still about classification, but you have more method to try. And then the last one is going to be I think reinforcement learning. Basically, you will develop a model to play some games, and then the performance of your games is going to be your score. Okay, so if there's no more question, then I will see you again next week. Thank you.